Hello, and welcome to our presentation about toughened epoxy adhesive for structural bridge repair applications. 2K epoxy adhesives are widely used for many structural applications in construction due to the advantages which are given by this technology. These are high mechanical strength, durability, and the possibility to bond a wide variety of substrate without any pre-treatments like, for instance, primers. But one of the limitations of the epoxy technology is the rigid nature, which isn't a problem when bonding on concrete because the concrete is even more brittle than the adhesive. But when bonding other substrates like steel or carbon fiber reinforced plastics, the topic becomes more relevant. This can be seen in the 3-point bending test which we made, in which we bonded an F4P plate on a steel plate using a standard epoxy adhesive. While pressing down this sandwich, the bonded line isn't capable of withstanding the loads and simply pops off the steel substrate. We wanted to overcome this hurdle, and therefore Sika has implemented a new and patented toughening technology from the automotive and wind industry into a 2K epoxy adhesive for construction. This technology allows us to combine the known advantages of epoxy technology with the advantages of flexible adhesives. And the main idea of this toughening technology is a toughening agent which is used in the epoxy adhesive and starts to separate while the adhesive is curing. And as a result, the toughening agent forms very small and well-distributed particles, and they are chemically linked to the epoxy matrix. The matrix itself is not flexible or flexibilized, but it contains small and flexible domains. And we can observe this when comparing the macroscopic picture from the standard epoxy adhesive on the top right to the picture of the toughened epoxy adhesive right below. If we now have a crack appearing in the adhesive, which here is indicated by the red arrow, it starts to propagate inside the bond line, and at some point it hits one of these toughening particles and the crack is being redirected into the matrix, and as a result the fracture energy at the tip of the crack is distributed inside the matrix. This effect, which I just described, can be shown in a 3-point bending test of a toughened epoxy adhesive. By pushing down the adhesive bar, we increase the force and the crack starts to propagate. And we can observe the energy at the tip of the crack is being distributed into the matrix by the appearance of the stress widening, which can be seen all around the tip of the crack. And as a result, it requires more force to make the crack propagate through the adhesive. To show this toughening effect, we've made a fatigue test, which is made by bonding lab-shear test specimen, which in this case is made of CRP, and exposing it to a cyclic load at different stress levels. The x-axis shows the numbers of cycles the test specimen survive at a given maximum load, and this maximum load is shown in the y-axis. The red line represents a standard epoxy adhesive, while the green one represents a toughened epoxy adhesive. And when we compare both lines, we see a shift towards higher cycles when using a toughened epoxy adhesive. And if we compare now the number of cycles survived at the maximum stress level of 12 megapascal, the specimen bonded with the standard epoxy adhesive breaks after 330,000 cycles, whereas the specimen bonded with the toughened epoxy adhesive survives up to 2.8 million cycles, which is an increase of the lifespan of 8.4 times. We have again made the same test using steel plates, but this time we've compared welded plates with plates that have been bonded with a toughened epoxy adhesive. The yellow line shows the welded plates and the blue line the steel plates bonded with the toughened epoxy adhesive. And we can see that the curve for the substrates bonded with the adhesive is much more flat, which means the lifetime is increased towards lower stress levels. If we compare the cycles survived at the stress level of 7 megapascal, the welded substrate survived roughly 500,000 cycles before the substrate breaks, whereas the specimen bonded with toughened epoxy adhesive is still intact up to 4 million cycles, which is an increase of the lifespan of at least 8.3 times. Finally, we have made another test to show the suitability of the toughened epoxy adhesive to repair a crack in the steel plate. In this test, we have exposed the pre-cracked steel plate, as shown in the top right corner, to cyclic loads again. The specimen has a crack in the center with an initial length of 24 millimeters. And during the cyclic load, the crack grows towards the edge of the steel plate. And in this graph, the x-axis shows again the load cycles number to which the specimen has been exposed, but the y-axis this time shows the length of the crack inside this steel plate in relation to the number of cyclic loads. The black curve shows just the cracked steel plate, which is the reference. The yellow curve shows the cracked steel plate strengthened with CRP plates on both sides, and the orange curve shows the cracked steel plates strengthened with CRP plates, which have a pretension of 6 kilonewton. The CRP plates have been bonded to steel by using a toughened epoxy adhesive. And as we can see in the graph, the crack inside the reference specimen reaches a length of 50 millimeters after 40,000 cycles, whereas the reinforced plates require up to 360,000 cycles to reach the 50 millimeters. This is an increase of the lifespan of up to 9 times compared to the reference.
Bridges are vital parts of infrastructure in any modern society. In many parts of the industrial world, the rapid industrial development that took place during the first half of the 19th century was accompanied by a huge expansion of the infrastructures, including the building of several bridges. Today, many of the railway and highway steel bridges built in that period are still in use, despite the fact that their technical lifespan is, in many cases, deemed to be already completed. A mapping of the age profile of existing steel railway bridges in Europe shows that more than 70% of these bridges are more than 50 years old, and about 30% of them are more than 100 years old. Furthermore, this aged stock of railway and highway bridges is currently being subjected to more rigorous demands in terms of increased traffic intensity and high traffic loads in order to meet the requirements for more efficient transportation systems. On railway or highway steel bridges, fatigue is a major problem, limiting the load carrying capacity and the residual life of existing structures. Fatigue causes cracking-induced damages. This damage starts as a microcracking and then grows up and extends with load cycles up to element collapse. Typical solutions used to solve these issues can be welding the crack, creation of holes to stop cracking propagation, or adding some steel reinforcement with fasteners or bolts. These solutions add some additional weakness to the element, drilling the holes, for example, or repair the damage with something, the welding, for example, which hasn't an optimal behavior with fatigue and cyclic loads. I would like to show some possible alternative solutions using toughened epoxy resin Cicadur 370 for fatigue crack repairs. Using the toughened epoxy technology, we can repair or strengthen the bridge or the steel element, can be a beam or can be a tendon, ensuring very good performance in long-term cyclic loads, and in this case, we won't drill any holes. Elements with curved ends and cut short flanges are commonly subjected to fatigue cracking, as shown in the drawing and in the pictures. This crack appears slowly and then propagates fast. It's possible to repair the crack bonding some steel plates or some pull through the carbon fiber plates using toughened epoxy adhesive Cicadur 370. In connection between grinder splices, fatigue cracking can appear close to weldings, as shown in the drawing and in the picture. Even in this case, it's possible to repair the crack bonding some steel plates or some pull through the carbon fiber plates using toughened epoxy adhesive Cicadur 370. In case of welded cover plate reinforcement, fatigue cracks can occur at the end of the reinforcement plates. With the same approach seen in the previous slide, it's possible to repair the crack bonding steel or carbon fiber plates using the toughened epoxy resin Cicadur 370. Or it's possible to reinforce in flexure using pultruded carbon fiber plates to steel beams or to increase the tension capacity of steel tendons using toughened epoxy resin Cicatur 370 with higher performance and long-term resistance than traditional structural epoxy adhesives. Thank you.